Good morning, mathematicians. Okay. Took me a second because for some reason it wasn't working and I was getting different error messages each time I tried to hit stream. So, as you notice, my mic is back on a stand and my beautiful face is in HD definition. Because we're leveling up here. We gotta start acting like a channel that's got 10,000 subs, because we're about to be a channel that's gonna stand. Oh, and yeah, 10,000 subs. Anyways, spectral sequence time. As has been the case of late, that's what we do here in the mornings. We do spectral sequences. And oh, I paused my own beautiful faces in HD. Fixed mic. Is that better? Is mic working now? I mean, it was on before, but maybe it was just automatically set to the wrong thing. If anyone's as old as I am, maybe they know the quote. There, is that better? You sure input is coming from that mic? No, I'm not sure. Sounds like a fishbowl. I see. It could be... Right. No, it's not that mic. There we go. There we go. You're under 50? Yeah. Yeah. It's interesting why my audience is so young, these young children. And here I am, a grizzled old man. I guess you come to me for sage wisdom. This is the correct vibes for a math stream. What, having technical difficulties? It's funny, someone was saying, because there's some defense that was, now it's input from both? Oh, Lord. How about now? I mean, reverb's good. I like post-rock. I listen to post-rock. But, you know, there's someone's defense that's being organized, and, you know, one of the profs was talking about how, you know, because they've sat on committees before where there was like, you know, review, you know, someone maybe failed their defense and then tried to challenge it, and apparently one of the things that they were saying is that, oh yeah, one of the reasons they don't, you know, they make sure it's all in person now, not over Zoom, is because like students can cite the anxiety of the technology not working affecting them. And I'm like, you know, and I just said, I was like, well, okay, whatever, that's a policy. But I'm like, if you can't handle the stress of technology failing during your exam, how are you going to react when you're teaching in a lecture hall in front of like 200 18-year-olds on your first day and the technology goes wrong? Because this will happen. I feel like that should be part of the test, right? How do you handle pressure like that? Um, Whatever. You watched Reel's talk on formalism, and to be honest, it was great. Although you found it funny that the second guy said the proof that CH is independent of ZFC gave no intuition at all for why this is true. Oh, really? What does that even mean, though? Like, what about the independence of the parallel postulate? Does the proof give intuition for why it's true? It's like because there's other geometries. Couldn't you just say the same thing? It's like, oh well, there's other set theory. I don't know. I don't know enough. It's like one time my master's supervisor, I remember him trying to explain to me something to do with like lattices and Fourier transforms, and something about the dual lattice had something to do with the Fourier transform, and then he sort of like said this statement as a punchline, and I was like, man, I'm so lost. I don't know enough to be amazed by the statement. So similar way, it's like I don't know enough to be lost by a statement. Mike still doesn't sound great. What the hell? I wonder what's going on. Huh. Give me a second here.
Okay, how about now? Please tell me this is good. Okay. Let's get into the math. You still don't have the guts to do board presentations? Your slides, bro? Oh, man, you gotta level up. You gotta level up. Okay. Right. I remember we left off on me being confused about this. So assume there is a finite length. Hello, Fimno. Finite length kg resolution. Each finitely generated permutation module. Again, what does that mean? Like supposedly, I guess you can hear colors now. Good. Can you see sound? I was told this camera would allow you to see sound. Okay. So, really, it should break up as a sum like this? Sure, I don't know why, but okay. You gotta eat a big bowl of slimy goo. So you'll be in and out the next 15 minutes or so because you can't touch your keyboard with the goo. Don't you have like protective wrap to wrap it in while you eat your morning goo like all other humans on Earth? Okay, let's just look at this for a second and then yeah, and which is actually very interesting. Like, it's very interesting to me that this person knows about spectral sequences. Obviously knows way more about spectral sequences than I do, but they don't know about /Tor. Like I said, we might have to go over to Viable soon. Okay, homology is defined like this. Converging spectral sequence of Brown's cohomology of groups. Oh, okay. We have a converging spectral sequence. Okay. Lilo plus? Okay. Let's, here we've got an example. We've got a presentation of the quaternions. We've got a presentation of the quaternions, and each one of them is normal. Each of these subgroups is normal. More precisely, is the Unicode plus character. It looks smaller than O plus. Weird. More precisely, Q8 is a group of order 8, cyclic maximal subgroups. Therefore, the derived group is this. Abelianization is this. Okie dokie. Okie dokie artichoke. Okay. So, we know that... Wait, why do we know this? I am a group of... I'm the quaternions, Leo. Don't you dare tell me I'm abelian. Don't you dare, you'll get banned if you call me abelian. Wait, why is H1 just the group HOMs? That should be H0. Did they mean H0? H1 is the group HOMs? I find this to be unlikely. Certainly this is a typo. Yeah. It must be a typo. Okay, but that's the same because all those HOMs have to factor through the abelianization. So H0 is the Klein group. They must mean H0. So that is the dual space. What? H naught is the invariance. Oh, sorry, you're right, Femnol. You're right. Actually, H naught is the invariance. You're absolutely right. H naught is the invariance. Let's see here. Where did I write down? Okay, let's go through and let's think a little more carefully. Where the invariants, or I mean, we wrote down our formulae for our cohomology groups previously. No, I guess we just gotta compute it, right? I guess we just gotta compute it in this case. So what is, okay, hang on. So H1, Q8, C2, I mean, it's going to be Q8 squared into C2. I'm pretty sure H1 is the morphisms. As you texted, your friend took intro algebra. No, this can't be true in general. There's no way that this is true in general, right? 'Cause there's no way. There's no way that this is true in general, right? Like, these are... oh, hang on. H1, sorry. So this should be a morphism... this should be a morphism into C2, sorry, from one copy, Right, and we should have, right, f gfh minus fgh plus fg. Right, and this is the trivial action. Right, this is the trivial action specifically in the QA case. Okay. I'm good with that. Prove that x being greater than 3 and less than 2 implies this inequality. I don't really want to. Can I help you here? Because the solution is, since x minus 2 is less than the absolute value of x plus 2. Okay, whatever. I'll take a look. X between here implies the absolute value of x squared plus x minus 6 is less than 6 x minus 2. I mean, this thing in the middle factors, right? X squared, or sorry, x plus 3, x minus 2. So that's a key part of it, right? Probably cancel these x minus 2 factors. So really it should just be, yeah, the absolute value of x plus 3 is less than 6. Basically just a consequence of that, right? How is x plus 3 becoming 6? It's not. It's less than 6, right? X is less than or equal to 2. So x plus 3 is less than or equal to 5, which is less than or equal to 6. So the same is true of the absolute value. If it's Abelian, it should be true in general? No. Absolutely not. Absolutely not. Because, if the action is trivial. If the action is trivial. But that's a key part. We're all dumb. Seek, that's why we're here. That's why we're gathered here together today. Just at different stages of the dumb. We're all trying to undumb here. Okay. So, so H1 is the dual space to the F2 vector space with this basis. Sure. Hence the dual basis is made of the following maps. Okay. Abelian is nonsense? What do you mean? Abelian is beautiful. Just don't call me Abelian. From the third assignment. Oh, this is someone's homework. It's secretly a your proofs are trash video. Except I can't really comment because I don't understand what's going on yet. By the way, new proofs are trash video coming soon. Also, someone commented, no one's bought any Piata cats yet, but someone commented they would buy a mug, so I don't know what kind of mug I should make. Maybe Piatic ones. If I were a finite group, which would I be? Well, Leo already said I was a group of order 8, and I wasn't abelian, so that leaves 2 choices, and I don't feel very dihedral. So, let's say the quaternions. I'm in love with PSL 2.7 though, so I don't know. Okay. Wait, from the third assignment, we know this? Okay, so I guess I'll just take that on faith. Yeah, maybe I should go to Bible instead of reading somebody's homework. Was W in degree 1 as seen in class. Then we have the Knuth formula. Wait, can we really do that with product groups? Interesting. Knuth formula and group cohomology. Yes, trivial action is a thing you should have said, Femnalia. Right. Oh, interesting. Right. Okay, so we sum up against these. What does it mean, tensor over M? Huh? What? What does tensor over M mean? Huh? Huh? What the hell do you mean tensor over M? Brown's cohomology of groups. Assuming either of these are free, then we have this. What if they're not free? Oh, this is a sequence. What? Where's Brown? I have it right here. Okay. Let's have a little look-see at what Brown says. I know this is very exciting for you all. I guess I can, my camera is now mobile. It's this little thing, so I'll show you in a second. Where's the Knuth formula? Pointryagin product. Spectral sequences. What? My eyes are deceiving me. I see no Knuth anywhere. Unless, does he not call it a Knuth formula in this book? But that would be crazy, right? There's no way that that's true. Oh, Knuth formula. 109 and 120. Okay. Let's have a little look here, gang. Come along with me. We're on a magical ride. We're on an adventure. Okay. Let's see. What's going on here? Homology cross product. Given special case, there's an induced cohomology. Okay, that just says there's a product. Where's the show that the map 2.1 is an isomorphism. Wait, that's map 2.1. Deduce under suitable hypotheses that there's a Knuth formula for computing this in terms of this. Okay, he doesn't even tell us what the formula is. He just says under suitable hypotheses there is a formula. Okay, what about on page 120? Oh, I wasn't looking at how the camera is pointing. Is this even legible? I have no idea. If G and G prime are abelian and K is a principal ideal domain, principal ideal domain. Yeah, I guess it is. So we tensor over K. Very strange. Okay. Well, I'm going to have to make a video on that sometime, using that to compute some stuff. Mostly illegible. Okay, well, whatever. At least we had fun, right, guys? Right, gang? Right, gals and NBs? And AI bots that are also here. You have more MSE rep? Yeah, I don't have... this is my overflow rep. I have more Stack Exchange rep. Not that I don't remember the last time I answered a question, though. So you probably have more MSE rep than me as well. I've asked a lot of stupid questions. Yeah, see, my MSE rep is higher. Is there no PDF? I don't have a PDF of Brown. Do I know maths used in Iron Man armor? What? I don't know what you mean by that. 100% whatever math you saw in the movie is probably BS. Is there images? Yeah, I don't know what you mean. Math in Iron Man's armor. I don't know what you mean by that. Probably nonsense. It's exactly the same as the Kunith for spaces. Isn't it simpler for spaces? I mean, what's... Oh, yeah, because I guess it is just... I guess it is just... It literally is cohomology of certain spaces, right? I guess... Okay, so it's... Okay, because it's coefficients in a field, it should just be this, right? We don't need to worry about this principal ideal domain, higher Tor nonsense. The higher Tor nonsense should vanish for us, right? just got stunted on, yeah. Don't forget it, Boris. For basic set theory series, you're doing a tier list of all set theory symbols. Bonus points to whoever can guess the only one to get F tier. I don't know. I need to make some tier list videos as well. Set minus is pretty bad. But, okay, wait a second. I'm confused. Right, okay. So this tensor product, it needs to be, you need to be taking coefficients in a ring. You need to be thinking about the ring structure here. Disjoint union is the best symbol. So strong and manly. Yeah, it is very fortuitous. It's actually a fun exercise. Fields have global dimension 0, so the Kunith spectral sequence. Oh, this can also... oh, that makes sense. I guess this is proved with a spectral sequence. Interesting. PIDs have global dimension 1, so it survives one page, etc. Oh, very interesting. How would I show that A plus B is bounded and closed if A and B are subsets of Rn? Well, that's not going to be true in general. Just take A and B to both be Rn. So... but you could take I mean, the number one, the answer is to cheat. Yeah, as well as I was gonna say, uh, uh, um, the first move is to always try and prove it from definition. Okay, A and B are bounded. A and B are bounded. Okay. Well then, I would guess that, like, I could be wrong, but if M and N are upper bounds of A and B respectively, then I would guess that it's not too hard to show that M plus N is an upper bound of A plus B. Right? So what do you need to show? You need to show an arbitrary element of A plus B is less than or equal to this. I did not know Pontryagin was blind his whole life. You've chosen delta for symmetric difference as your unique F tier. Wow, Leo, you're so wrong. I can't believe. Yeah, I couldn't disagree more. Delta is awesome, and symmetric difference is awesome, and delta for symmetric difference is awesome. Can you use virus stress? What? No, I mean, what's the definition? So what do we want to show? So I claim that this is a bound, right? I claim that this is a bound. So what do you want to show? So we want to show, we're trying to prove that for all x in A plus B, that x is less than or equal to m plus n. Okay, so how do we start the proof? Let x be in A plus B. So, wow, Leo, you're really trying to get yourself banned from this channel pretty hard. Symmetric difference is everything. Symmetric difference is awesome. Hi, Mom. Love you. Yeah, symmetric difference is awesome. You don't know why the stream was recommended to you? You barely passed Calc 2? Well, because it's time to level up. The algorithm knows that that you got that math dog in you secretly, and this is your chance to level up. Here's why the symmetric difference is awesome. Take a graph. Take a graph, and then consider. So first off, both of the first off, for any set, take a power set, and this becomes an abelian group under the symmetric difference operation. So that already is interesting to me, and now we're getting into like Boolean stuff. And then, moreover, take a vertex set of a graph, and we get a vector space called the free vector space on vertices. Well, you can also just view it as the symmetric difference specifically. So okay, over any field you can take just the free vector space. But specifically, if you work over the field F2, then this just becomes the power set. This becomes the F2 vector space given by the power set on the vertex set. Same thing with the edge set. And then, so this is like a fantastic use of this. And in particular, one gets a difference operator between edge space and vertex space in this way, and the kernel of this operator is the first cohomology of the graph with F2 coefficients, which is also called the cycle space. And now we have this very interesting vector space, and it gives us an invariant of our graph, in which the literal elements of this vector space are Eulerian subgraphs. All of these you shouldn't use delta. Why not? Delta for difference. I mean, what do you think should be used? I mean, mind you, to be fair, I often use just an ordinary plus because I think of these things as vector spaces. But we all love math here. You mean math? Well, maybe both. How can you do one without the other? Boris is enlightened, maybe, but he could still be wrong about things. Saw a cool algebra qual question. If you want to flex on the haters, G is the union of, G and G. Oh, G is the union of conjugates for some subgroup. If G is the union of conjugates of some subgroup, then prove that H equals G if G is finite. Your initial idea was to find contradiction to finiteness, but it didn't work. Well, this is spectral sequence live stream, so I kind of, I'm tempted. I kind of want to get back to the spectral sequence stuff, but that is an interesting question. Why not? You're confused? Well, first off, why would you want to use Weierstrass? You can find a subsequence. Whoa, why are you talking about subsequences and limit points? Why are you talking about subsequences and limit points here? So what do we need to do? So this is the statement that we're trying to prove. We're just trying to prove that for all elements of A plus B, X is less than M plus N. That is it, right? And so what do we need to do? How do we start a for all proof? Well, we just pick an arbitrary element of our set. Okay. Now that we have an arbitrary element of our set, what can we say about it? All right, what's the definition of A plus B? What does it mean? If you use delta, there's a lot going on in chat. Yeah, okay. Don't know if there's an example where it fails for infinite G. Okay, I'm gonna write down. I'm just gonna write down the statement. I'm just gonna write down the statement, and then we'll get back to spectral sequences. If G is the union of this, and G is finite, then H has to be equal to G. Okay. Plus checkmate? No, you didn't checkmate me at all. I'll ban you. How about that? No, I'm just kidding. Or am I? You've seen like one valid use of delta, which is like bounding the difference. No, come on. Terrible. If you don't like delta, you're not gonna like my new categories of modules video. Doesn't have to be a delta though, it's a triangle, yeah. This is like people who use epsilon for membership. Yeah, that's horrendous. Because it feels easier. It's like 7 lines or less. I mean, I think Matthias, this proof is like it's only a couple lines, and there's no need for limit points or anything. So again, we're right here. What can you just say? Like don't make it more complicated than it needs to be. We have an element of A plus B. What does that mean by definition? Unpack that definition. Okay, but let's come back to spectral sequences for a moment. This is the spectral sequence live stream after all. So whatever, we've got our Kunis formula, gives us this thing. Got this quotient group. Now the quotient group acts trivially. The quotient group acts trivially. Whoa, why is that? I don't understand. I don't understand this line of reasoning. I guess because it's a central extension. Because I guess, I mean, I don't even know necessarily the point about the because it's the, I see. Okay, it's the commutator acting on this. Okay, so the quotient group acts trivially on here since this is the center. Right. I mean, yeah, I guess it's another way of just saying that if you look at the action induced from the Klein-4 group on here via the short exact sequence, it's just the trivial action. And so, okay, it should lift to the trivial action in cohomology. But why is this the E2 page? What? Therefore, the E2 page, was this just the definition then? Or what's going on here? Oh, yeah, because, let's see. What are the Qs? These are Q8s. These are, this is the Klein group. Or, sorry, quaternions. Group of quaternions. Right. This is just the definition. Right. Okay. But then we're saying that this is the trivial action, so we know... Oh, wait. How are we getting a tensor product? Oh, what's going on here? How does this become a tensor product? A short exact sequence of groups gives a fibration of their classifying spaces. So this coincides with Serre. Wait, is that how we're getting the... Is that how we're getting the tensor product here? That's actually... Wow, that's actually a really cool idea. That's actually so cool. I mean, it's basic, I guess, but using the fact... using that a short exact sequence of groups gives us a fibration of the classifying spaces. Okay. All right, everyone's talking about this problem in chat, so let's just talk about this problem in chat. Wouldn't one get that the sum of the size of all the conjugates of H is G? This is true. So the sum... No, that's not true. That's not true, Leo. It'd definitely be bigger than G. Right? There's no guarantee that these are all disjoint, right? But we could say something like if we divide it out by the size of the stabilizers, right? So it's like if G is the sum of what's a right way to phrase it? If G is the union of these things, I mean, basically it's the sum of each of the distinct, maybe there's like I equals 1 to N, GI, H, GI, inverse, right? So then it's like, what's the sum of these things? So that'll be the size of H times, I guess, the number of orbits. Times the number of orbits. Where, I guess, the set we're looking at is the conjugates of GG inverse. Right? Something like this. Yeah, G equals H times stabilizer. Right. And then, yeah, I mean, we also have that G should be the stabilizer of H times the orbits of H. So then we get that the order of H is equal to the order of the stabilizer, but of course H is a subgroup, so all of the H's stabilize H. No, what are we doing? Wait, what are we trying to prove? We're trying to prove that H is equal to G. What's the theorem? H is equal to G? Right, if G is finite. We don't know H is normal. Right, exactly. But H is normal in H. Sure. Yeah, let's see. Definitely this is some orbit stabilizer theorem type beat here. Honestly, Leo, I don't know what your proof is. You got a normalizer here. You got, what are you saying? If they have any intersections at all, H is a proper subset. But I don't see why it follows that the sum would have to be less than the order of G. Let's see. So, right. Every GH G inverse has identity. I mean, that's true. I misunderstood your question about the weirdest field. Okay, we got a callback to like several days ago. You said you may mean division algebra. Yeah, I saw that comment, and I did, but I went back afterwards and I saw that comment, and in that live stream, I then gave you an answer. Well, kind of, but not really. I mean, I ended up, after I saw that comment and corrected myself, I was like, well, I don't know. Yeah, it still doesn't. Well. One, I don't know, because I feel like I don't know a ton of division algebras, so I don't know. They're not that weird. I don't know any really truly weird ones. Other than like what, p-adic quaternions or something. Oh, you didn't watch the whole stream. It was a couple of minutes after you asked, but yeah. Yeah, I don't have a good answer. Your answer is, yeah, that's probably weirder than what I would have come up with. You think your original proof works as soon as you realize G is less than or equal to the order of the stabilizer? I mean, that's definitely true. We know that, but I still don't understand. I don't understand what your proof is. I don't understand what your proof is. Oh, I see. Hang on a second. Right. I see. Okay. Right. Because, I mean, just by application of the orbit stabilizer theorem, we know that the order of G has to be less than or equal to the stabilizer. But the stabilizer is, of course, a subgroup of G, and so therefore that's only possible if the stabilizer of H is all of G, and so that implies then that this union therefore is really just H, and then that does it. Nice. Okay. Okay, back to spectral sequences for like 10 minutes or something. It's something that came up in conversation with a friend. He said that tensor products of function fields of algebraic varieties and positive characteristic is really weird to work with. Interesting. I didn't know that, but maybe one day I will understand why. But if the orbit is bigger than 1, there are intersections at the identity, which subtracts from the count. That's definitely not your proof or valid. Wait, did I make a mistake? Is there something wrong with what I said? If the orbit is bigger than 1, there are intersections at the identity? I don't get it. Also remember that for an irreducible topological space, the continuous functions from X to a field. Wait, what does that mean? To a field? To a topological field? To any topological field? Forms an integral domain, and so it has a field of fractions. From any topological space to any topological field. Okay. Yeah, Leo, I still don't get your point. H is not necessarily normal, sure. I didn't use that anywhere in my proof, though. So an arbitrary, complicated, irreducible topological space leads to an arbitrarily complicated field. I'm not understanding any of chat today. Yeah, an absence of topology take locally constant. Sure. Yeah. Okay, where are we here? Where are we in spectral sequence land? Okay. Maybe this is coming from some Serre stuff, but maybe we should switch over to Weibel soon. We used universal coefficient to get the first isomorphism. We want to compute the image of this spectral sequence. If the orbit is bigger than 1, the class equation is weird. That's why you initially said conjugation must be trivial, so transitive. What? Oh, you're absolutely right. I see. You're absolutely right. I made a ginormous Dumbo mistake. That was really dumb. That was super dumb. Actually. Does Serre's local field have common content with his book? I don't know. It's been so long since I've looked at Serre's local fields. I feel like I'm gonna change the title of the stream from spectral sequences. I'm just gonna call this a normal office hour, I think, afterwards, because it kind of turned out to be that way. Yeah, I mean, I know you could take continuous real valued functions, but you made a statement about any field. And I was surprised about that statement about any field. But two such functions cannot have disjoint supports, as X is irreducible. Okay. Okay, let's let's return to this question then and try to be less dumb. Okay. We do have orbit stabilizer theorem. We do have orbit stabilizer theorem. On to so the stabilizer of H, maybe there's some normalizer stabilizer stuff we can do, and then the orbit of H, and then over here, right, what's going on with this sum? Well, what can we say? Right, I already wrote it out in this distinct way for the number of distinct H's. But we could say what? Right, so I mean, this still is going to be the order of H times the number of orbits. I mean, this much is still true, and so what? This just tells us the stabilizer of H. This tells us that the order of the stabilizer of H is H, and so that tells us that H must be its own stabilizer. Okay, so this tells us that this tells us what? That there, right? That all the other elements of G have to send this other places. Okay, maybe I understand what you're trying to say about the identity now, right? So you're saying the order... Okay, let me write out your equation here. So meanwhile, Leo, you're saying G, which is the order of this union, is less than or equal to the order of H times the number of orbits, times the number of orbits. Yeah, I mean straight up equal to, right? It should be straight up equal to. Unless I'm losing my damn mind. Which is less than or equal to NH times the number of orbits? What do you mean by NH? Do you mean the normalizer of H? H may not be its own stabilizer. But it has to be. Right? Like, okay, where did I go? Then where did I go wrong? Where did I go wrong here? Because certainly this should be equal, right? I've already partitioned it up into the number of orbits. So, and the cardinality of this thing is just the cardinality of H. And so we have the cardinality, so it's going to be the number of orbits times the cardinality of H, and then going this way around the equation, we conclude that the cardinality of H is equal to the stabilizer, the cardinality of the stabilizer, and we know that every element of H stabilizes H, and so they have to be equal. Which is, of course, I mean, this is part of the, this is, like these things are going to be equal, right? Because at the end of the day, we're showing that H is equal to G, and of course, the stabilizer of G and G is G. G should in general be much larger than the size of the union. What? No, the other way around. The other way around. The size, sorry, you're right. You're right. In general, G should be the much bigger than the size of the union. But I'm not using it a priori, right? I mean, I'm using the assumption that G is this union. So where did I go wrong in this implication? NH is the set of all things that fix H. Okay. Part of the proof of the statement is that those things aren't equal? You're doing all cases? I don't understand. The assumption that G is the union is not justified anywhere. That's part of the assumption. That's the assumption of the question. That's the assumption of the question, is it not? Right? Where's Boris's question here? Yeah, if G is the union of all of these. I mean, this is part of the question. Do we have a Discord community to discuss or share ideas, or just YouTube? The live stream happens basically whenever I start it. I don't have a set time, and I don't think that's going to change anytime soon. Sorry about that. I did just start a Patreon. I haven't started advertising or sharing the link yet, but I am going to start a Patreon. I was going to put it $1. Just to buy me coffee. You don't get anything. I was going to put $5 for Discord. I don't know. Maybe that's a little steep, but I don't have anything else to offer you guys at this point in time. I'm starting to put videos out early, so maybe, that could be part of the see videos early tier or something. I don't know. But, so just keep your eyes open for channel posts and stuff. I'll probably start linking it in the descriptions of videos. Okay. Well, now I think, hopefully no, my proof is not complete. I'm not claiming that my proof is complete. I'm only claiming so far that I've obtained the statement that H is its own stabilizer. That's all I've got. Well, yeah, but H is not only are the orders equal, but it's straight up, right? Because of course H stabilizes itself. So, and we're assuming here everything's finite. So if H is a subset of the stabilizer of H and their orders are equal, they must therefore be equal. I don't understand your way, Leo, though, to be honest. We're like, and didn't you just say you're doing the contrapositive? So I don't understand your approach. Showing in the case orbits bigger than 1 implies the size of the union is less than G. Yeah, I don't understand. Yeah. So if the number of orbits was bigger than 1, will I meet all the Patreon members at ICM? I don't even know if I'll go to ICM. It seems easier to do H's subset of G implies the union is strictly less than G. But that, why is that though? Why is that? Because of counting and such? Okay, so if we assume that H is a proper subset of G, then what? Then the union, then the order of the union What are you saying? Because of the proof you did earlier? How much would I charge to talk at your department? I don't know. The cost of a plane ticket? 2 plane tickets? Or I could just give a talk on Zoom. But I don't know, is there anyone in your department that'd be interested in like the stuff I'm doing? I'm slow, Leo, so you gotta, explain these things to me carefully. The order of the union of these is less than or equal. Okay, but it's actually straight up equal to this. I mean, we've already argued that it's straight up equal to this. And okay, which is equal to the stabilizer. Then because of intersections at the identity, the union must be smaller than G. Okay, so hang on. So here we've got, I mean, what you're calling NH is the stabilizer of H, right? What you're calling NH is the stabilizer of H. And this is equal to G. This is equal to the order of G. But we've just gone in a circle because we knew that these things were equal by assumption. So if the orbits are bigger than 1, the union must be smaller than G. Okay, yeah, H is a proper subgroup of G. Check. Contradiction proof. This is part of the assumption, though. This is part of the assumption, right? This is part of the assumption. So where are we getting a less than or equal to? Because this is also just true, like these equalities are all just true regardless. Oh, I see. Because you're saying, no, I still don't understand. I still don't understand what you're saying. We're very confused about an algebra problem. Well, what do you mean forget about the assumptions? Then what are we doing if we're not making the same assumptions and trying to prove this? Okay, in general, sure. Okay, whatever. I'll just humor you. H is a subgroup. H is a subgroup of G with G finite. Okay. I'll humor you on this. A high school homework puzzle? I don't know if I would say I don't know many high schoolers that could do this. Okay, H is a subgroup, G is finite. Everything you wrote down is true for all subsets. G. Okay, so in general, you're saying that the union of G, H, G inverse is less than or equal to okay, so wait. I mean, this is definitely going to be straight up equal to H, the order of H times the number of orbits of H. This is definitely true. Now say that the orbits are greater than there's more than one orbit. Okay. So where are we here in this proof? H is a subgroup, G is finite. The order of this union is equal to H times the number of orbits. Okay, yeah, all of these, sure, the identity is in there. I agree. The disjoint union of all of those for each member of the orbit is less than G. Wait, I don't understand this comment. The disjoint union but how, why? Why is this the case? The size of the disjoint union. I see. Right. Right. I understand now. I finally understand now. Wow, that took an embarrassing long time. And now I'm going to keep it on the internet forever. Right. That was this part of the argument. Because it does have to be less than or equal to, and it is strictly less than. Yes. Okay, now I see what you're saying because of the double counting. Holy moly. We got there. Gang. Wow, someone should revoke my master's degree. Probably. Okay. Just edit out the whole middle and get it immediately. No, I'm too honest for that. Okay, I guess we'll leave it there and edit it, so I'm explaining it to you, yeah. I guess we will leave it there, and we'll return to more spectral sequences tomorrow. So thanks everyone for bearing with me. And QED.